Akka is a toolkit for building concurrent, distributed, message-driven applications on the JVM. Akka provides an implementation of the actor model of concurrency, which simplifies concurrency by adding a lighter weight abstraction than threads and thread pools. Konrad Malawski joins the show today to discuss Akka and Reactive Streams. Reactive Streams is an initiative to provide a standard for asynchronous stream processing. This episode goes deep into modern concurrent programming, and it's a great companion to some of the shows that we have done about reactive programming and functional programming. Before we get to this episode, a few quick announcements. If you're interested in advertising on Software Engineering Daily, send me an email, jeff@softwareengineeringdaily.com. There are more than 14,000 engineers that listen to Software Engineering Daily on a regular basis, so it's a great place to get your product out into the ears of developers or to advertise available jobs that you might have at your company. Also, if you're an engineer that's looking for an open source project to work on, check out Software Daily at softwaredaily.com. This is an open source news and information site about software. It's being led by Jeff Tribble, a member of the Software Engineering Daily community. You can also check out softwareengineeringdaily.com, which is the website for this podcast. You can find links to the Slack channel, my Twitter account, my email. You can find a link to sign up for our newsletter, Software Weekly. And with that, let's get to today's episode. Life is too short to have a job that you don't enjoy. If you don't like your job, go to hired.com/sedaily. Hired makes finding a new job enjoyable, and Hired will connect you with a talent advocate that will walk you through the process of finding a better job. It's like a personal concierge for finding a job. Maybe you want more flexible hours or more money or remote work. Maybe you want to work at Facebook or Uber or Stripe or some of the other top companies that are desperately looking for engineers on Hired. You deserve a job that you enjoy because you're someone who spends their spare time listening to a software engineering podcast. Clearly, you're passionate about software, so it's definitely possible to find a job that you enjoy. Check out hired.com/sedaily to get a special offer for Software Engineering Daily listeners. A $1,000 signing bonus from Hired when you find that great job that gives you respect and salary that you deserve as a great engineer. I love Hired because it puts more power in the hands of engineers. Go to hired.com/sedaily to get advantage of that special offer. And thanks to Hired for being a continued longtime sponsor of Software Engineering Daily. Konrad Malawski is an engineer at Lightbend. Konrad, welcome to Software Engineering Daily.
Hello, Jeff.
Let's start by talking about Akka. Eventually, we will get into concurrency and reactive programming and all the other things that go along with it. But let's just start with, what is Akka?
Okay, so for those of you who have not heard about Akka, the basically one-sentence summary is kind of like Erlang, but on the JVM. That's like the shortest description one can give. But it's a bit more than that. So yes, it's a concurrency toolkit, and not only concurrency, but also clustering and distribution. So it's all built around the actor model. So actors are pretty much at the core of everything we do, and actors are basically a concurrency and distribution model that allows you to very easily to build concurrent and distributed systems because instead of thinking about threads, you just think about actors, and the only way actors communicate is through messaging. And turns out distributing message passing is, well, I wouldn't say trivial, but very native to the web. So it leans itself very well to distributed systems. And at the same time, it turns out that, well, the same concepts apply to just concurrent programming, because basically message passing between two queues is conceptually very similar to passing messages between two nodes, right? It's just a difference of, well, here we have a queue inside the same process, and there we have queues, well, we have internet, so it goes on the wire, but the concept is very similar. So instead of, maybe last sentence here, so instead of turning it like some people have in the past to make method calls go over the network, and then it starts going a bit fuzzy, we go the other way around. So we take what is native to the network, so message passing, and use that locally as well.
Why is the abstraction of an actor useful? Why don't we just use threads to manage our concurrency? What's wrong with that?
Yeah, so basically, threads are pretty heavy. So that's one of the biggest kind of differences with actors. So a thread, at least on the JVM, they're especially heavy because the stack depth is kind of pre-allocated for each thread. So a thread weighs more or less a megabyte sometimes. And an actor weighs, at least in the Akka implementation, more or less exactly 400 bytes. And that's all you have to allocate to have an actor running, and you get kind of the same behaviors. You get all the concurrency and parallelism you want, but you don't have a meg, wasting your space there.
Are there some aspects of threads that we don't need that are giving us that extra heavy weight around a thread?
Yeah, so actors are still running on threads, of course, but when you go really, really concurrent and parallel programming, you kind of realize that it's not like everyone is running all the time, right? And that's kind of what a thread is there for. It's there and it's running, and if it's not really doing anything useful, maybe it's sleeping, so wasting time, or maybe it's spinning, so again, wasting time. So what we do with actors is, instead of wasting time doing nothing, we just don't schedule the actor, and this time, which would have been wasted by the thread doing nothing, we allocate to another actor. So we're able to utilize the same hardware more efficiently than we would be able to do with threads. And maybe the biggest mind shift and difference between thread-based programming and actor programming is the share nothing concept. So in thread world, usually at some point need to pass some information from one thread to the other. And well, at least in the good old days, you would have a log when the threads meet and communicate, or you would have queues. So you basically start re-implementing Akka, and that's a big piece of work. So what we do in Akka instead is, instead of having these points where you meet and exchange this information or logs, we just pass messages, and turns out that is really, really efficient, because basically in the entire Akka code base, which is, a few 100,000 lines by now, we have maybe 2 logs, and that's only in startup of the entire system. And of course, locking slows everything down, and it causes all kinds of problems. So
just to really drive the definition of actors versus threads home a little more, because we've done some shows about this, and I think people remain a little bit confused about it. Speaking for myself, so is in the actor model, is there, for example, a single thread and multiple actors are sharing the usage of that thread?
Yeah, so that's the simplest case. In practice, you have a thread pool, so you have n threads, and n would be something around maybe 30, maybe 40, so a relatively small number. A bit more when you have cores on your system, but not much more. On the other hand, you have maybe 1 million actors, and that still runs perfectly fine. So yeah, it basically is a multiplexing mechanism.
Got it. Okay, it makes sense to me. Are there other problems around JVM concurrency that Akka solves?
I think most of the trouble around, I call it the good old way, which is also the Java way with threads and mutexes and these kinds of things. They really don't scale that well. So yeah, maybe you can survive 100 threads, but there's just no way you're going to have 1 million threads running on your system, right? So the biggest thing we address is just the scalability, but also, well, at least from my perspective, the ease of programming using actors. Because with threads, you kind of always have to think, with each method call, you have to think, oh, wow, will this method call be safe if accessed concurrently? Yes, no, maybe. And it gets really hard. So with actors, we have this we call it an illusion of single-threadedness. So the guarantee an actor gives you is that if you receive a message, so you get this message and you do stuff with it, and then you receive another message, and of course you can have some state inside the actor, right? So you have like a counter field, and on each message maybe you increment it. If you were to do it with just threading and multiple threads accessing the counter, well, you suddenly have to use maybe volatiles or maybe some locks and think about this shared state there. But with actors, we kind of take care of the memory visibility for you, and you have this illusion that inside the actor, it's as simple as programming in a single thread. So you can access this counter, you just increment it, you're done. And then the next message arrives, and even though you could be already on a different thread, because like I said, we're multiplexing, so you very often end up having a few messages handled on one thread, and then a bunch of other messages handled on a different thread. But from the programming point of view, you really don't care, because the actor model guarantees that you're safe to modify your internal state. So it's also simplicity, I would say.
Mm-hmm. So Akka, for those who still might be a little confused, is this library for managing concurrency in the JVM. It's written in Scala. You can use it in a JVM language like Java or in Scala. So in Scala, there was actually an implementation of the actor pattern by early 2006. But it didn't have ideal support for concurrency. So what was wrong with Scala's early actor implementation? What did Akka get right in its different implementation of the actor pattern?
That's a great question, and that's a great story as well. So the original implementation of Scala actors was done mostly by Philip Haller, and he's a researcher, right? So he was very interested in the actor model, and he implemented the model very much like it is implemented in Erlang, and very much based on the papers. And there is a very big difference in how Erlang, the VM, so the Beam VM, can do stuff with processes, and what the JVM can do with processes. So in Erlang, basically each actor is its own process, and that allows them to basically kind of don't care about the kind of blocking inside actors, or they can just await a message without hurting anyone else. And if they don't, so if you're an actor and you don't want to receive a message because you're not able to handle it right now, the original papers and the Erlang implementation, what it would do is it just puts it in a queue on the side, and it assumes that, well, eventually you will be handling that message. So you will just pop the stack and handle these set aside messages. So now let's fast forward to the Scala implementation. It implemented pretty much that, and turns out it's really not a good fit for the JVM. There's a few problems with it. So one problem is, so if I can't receive a message right now, because maybe I'm initializing, I'm doing something else, so it's being put on the side in this external queue. We call it the stash. And if you never pop this stash, well, you never ever take these messages out of the stash. So it turns out that's basically a memory leak. It's like a built-in by design memory leak, if you will. But in the Erlang VM, the thing that would happen is, well, only this one single actor crashes. But what happens in the JVM, if you would do such a thing, well, the entire JVM crashes, right? Because you have one single JVM process. If you run out of memory, everybody is dead. So that's one problem about it. And the other problem was, it was more an academic endeavor. So it wasn't really fast, and it wasn't really geared that much for concurrency or distribution. So the Scala actors never handled distribution, so you couldn't send messages over the wire to a different machine. And that's pretty much what Akka did right, I think. The observation that message passing, very much like in the Erlang way, goes very well both for concurrency and distributed programming. So the story about how the Scala actors got eventually deprecated was that basically the community realized, well, they're not that good and we shouldn't be really using them because people would run into these out-of-memory issues and stuff like that. And by that time, Akka was already popular. So the decision was made to deprecate the Scala actors, eventually eject them from the standard library, put them on the side. And Akka didn't directly replace it, so Akka is not part of the standard library. However, it is very much the go-to library if you want to do concurrency in Scala.
So I worked at a place 2 or 3 years ago where their architecture was kind of mostly Java, but had some message passing using Erlang, I think for mostly for the reasons that you're describing that are desirable, the actor model. They also did have some Scala in production, but it sounded like, you know, they were sticking with Erlang. In general, what are companies trying to accomplish when they use Erlang versus using something like Scala? Like, what are the strengths and weaknesses? I mean, obviously, the actor-based model in Akka is based off of these, or it draws inspiration from Erlang.
Yeah.
So, in what conditions are people still using Erlang as the message passing layer between their Java services as opposed to just using Akka?
That's an interesting question. And I also attend some conferences where you also get some Erlang people and then we get to talk. And it's very interesting how, because like I said, the one sentence pitch is that Akka is like Erlang. or OTP at least. So it's the standard library around the message passing in that sense. But when you start really looking into it, you notice that the ecosystem, for example, Scala is of course very influenced by the Java ecosystem. So Akka is again influenced by the Scala ecosystem, which is influenced by the Java ecosystem. And Erlang is very much its own word. So the biggest win, and on the other hand, also a big pain point for maintaining Akka, is all of the interop capabilities with all the existing Java libraries out there. And this is really, really a big thing because Java libraries are really out there for basically anything you just need. And on the other hand, the Erlang ecosystem, either you're already part of the Erlang ecosystem or you're likely not really going to go there. That's my personal, and well, that's what we see with customers. You rarely see a Erlang shop suddenly go and become a Java shop, and vice versa. And we also, I mean, it's a difficult question in terms of.
It sounds like a matter of taste rather than some practical reasoning.
Yeah, I mean, you can certainly do anything in one or the other language and model, but it is very much a taste thing. But maybe a random observation that I found, it's an ecosystem observation. So in the Scala and Java ecosystem, that's statically typed languages, right? And Erlang, on the other hand, is, not really typed. So again, it's a taste thing, but it's also impacting how people build these systems. So I was a bit surprised how people test Erlang-based systems. It's not that kind of many tier, okay, here's my unit test, here's my integration test, here's my full-blown integration test of the entire system. So I think the entire feel of the system is very different. And again, this loops back to this preference thing.
Right. So I want to pivot the conversation a little bit and talk about reactive programming. Can you explain what reactive programming is and why that's relevant to this conversation?
Yeah, so reactive programming, we're, I guess, in the middle of the hype around that word. Or maybe, I guess we're at the peak of the hype. That's my personal kind of observation on it. But what is it really? The answer is a bit tricky. So back in 2013, I think early 2013, pretty much we as Lightband, so Jonas and some other guys from the industry, so Martin Thompson was invited there as well, authored the Reactive Manifesto. And already then, so why did even the Reactive Manifesto came to be? Because already then in 2013, there was a lot of confusion what reactive actually is. So everybody was using the word, but everybody was using it slightly differently. So, people would call, for example, things like RxJava, this is the definite reactive programming thing, right? On the other hand, people coming from a more distributed systems background would say, yeah, but we react to failure, etc., etc. So there was a problem around the word being very, very overloaded. So that was already in 2013. And I think we're still having this problem of the word being very overloaded, mostly because it's become very popular. And also there's a bunch of projects which have the word reactive in the name, like reactive extensions or RxJava, or reactive Kafka, which we work on, or all kinds of reactive anything.
And React.js, which has nothing to do with reactive programming.
Yeah, exactly. And I mean, the actual origin of, let's pivot a little bit, because that's also adding to the confusion. So there's reactive programming, but there's also functional reactive programming. And people think that's the same thing. Well, actually, it's not. And functional reactive programming is very much originated back in the days in the Haskell community, but more recently, when it became popular as it is right now, it basically was revived by the Elm programming language, which is a nice front-endy language to kind of react on events, react on mouse clicks and stuff like that. And that wasn't really a new concept. This idea has been around for years, but it kind of took it to the mainstream. So now we have libraries like RxJava, Akka Streams, and maybe Reactor as well, which follow the functional reactive programming paradigm. But that's a piece of the pie, because that only handles the local abstractions, the threading things, but it doesn't handle reacting to failure, which really is when we think about reactive, that's really part of it, because you want to have a system that is able to react to increased load, then it can scale down again. So it's not just being an overpowered iterator, which FRP is. And I say that even being an author of one of such libraries, but really FRP is a small piece of the puzzle.
Okay, so just to give people a better idea for what is actually going on here, we could talk about data streams and reacting to those events. Maybe you could give an example of, a prototypical example of somebody who is doing reactive programming.
Yeah, so prototypical example. Well, I mean, quite honestly, Netflix would be the biggest example, I think. And they do it on all the levels, which I mean when I say reactive. So they do the scaling according to load. That's in my perspective, a part of reactive. And they also do the FRP threading model things, right? And it all then kind of pieces together. But it's this thing about you can't just do one layer in your stack reactive and call it a day, because yes, then you get some benefits and that's where you start out with, but eventually you'll notice that if a part of your stack is still very, very blocking, very monolithic, then you need to work around it, and this will quickly become the bottleneck. So the prototypical example, so the Netflix example, they still struggle with a part of the system being in the old ways, let's put it this way. And that's part of the challenge with reactive, to see how we can evolve existing systems into actual reactive ones, step by step.
continuous integration is so useful that I've started using it on my own personal projects. SnapCI from Thoughtworks has the fastest setup I've ever seen. I registered for SnapCI with my GitHub account, and after a few clicks, I had continuous integration pipelines set up for a Node.js application and a Rails application that were just sitting on my GitHub account. And I don't want my users to experience breaking changes, so I want to run a large suite of tests for my application every time I push a change. And SnapCI will run those tests quickly, in parallel, on a worker that SnapCI spins up and takes care of for me. Whether you have personal projects like me, or you work at a company that is looking for the perfect tool to improve the deployment process, go to snap.ci/softwareengineeringdaily. SnapCI embodies the lessons that Thoughtworks has learned from 20 years of software deployment, the same lessons that have been written about by Martin Fowler and Jez Humble. Check it out at snap.ci/softwareengineeringdaily. It would support Software Engineering Daily, and you would get to check out continuous deployment. snap.ci/softwareengineeringdaily. Thanks for listening. So I think of reactive programming, you can tell me if I'm wrong, as you're going from the paradigm of thinking about programming over arrays to going to programming over streams. So rather than having these fixed length series of data that you're operating over, you basically expect there to be a stream that has an unbounded series of events. You kind of may not know when you're going to get a new event. All you are guaranteed is that the events are going to keep coming. Would you say that's accurate?
I would say that's accurate for FRP. So that's exactly the functional reactive programming part of the pie. And I think it's a big part, but it's not the complete part. So when you look at Akka, that part is exactly what Akka Streams is about. So this has been the last 2 years or so of our development, and we also kickstarted the Reactive Streams initiative around in 2013 as well. And let's talk about Reactive Streams in a bit maybe. But Akka Streams is exactly that. So you have an possibly infinite stream of data, and you want to apply some operations on it. But then you suddenly realize, and this is where we were at some point in time, that, okay, we have a stream of data, we handle it. But then you have this situation of, okay, but the downstream consumers of this data can't really keep up with this stream of data. And when they get overwhelmed, the stream slows down, or even worse, it goes out of memory, it then crashes. So this exact situation is what led us in 2013 to kickstart the Reactive Streams initiative, which was and is basically a standard. So it's not something you implement directly, but it's a common kind of way of handling these streaming, communication patterns, I say. But basically, all these libraries, so RxJava, Reactor, Akka Streams, they were at this point that, okay, we have a stream of data and it's kind of flowing, but then you want to handle this overflow scenarios. And this is where really the big challenge was. And what we addressed with Reactive Streams, which has been released maybe a year ago as 1.0 and is on its way to the JDK actually as part of the Java improvement process 266, which is the more concurrency updates. So it's a protocol on a library level that basically defines how to handle this overload scenarios in a back-pressured and safe asynchronous way. So,
okay, let's take a step back before we get into Reactive Streams. Let's talk about back pressure. Can you define that term?
Okay, so back pressure, maybe a new word for an old concept. It basically is flow control, right? So flow control, a concept not really new to the software industry, but we have kind of forgotten about it in the recent years. So we did have these stream processing libraries. Like you said, you think about your app as this infinite stream of data, but somehow we forgot that, well, different parts of such a stream can have different processing rates, and then buffers get filled up, and eventually you get a very crazily GCing system. So back pressure is a way to control the rate of sending messages between these stages in such a stream in such a way that no stage is really overwhelmed. And by overwhelmed, I mean has to, for example, infinitely buffer. And you can't really infinitely buffer in a normal computer because you have limited memory. So we basically avoid out-of-memory issues. And yeah, let's talk about reactive streams in a bit, maybe.
Well, and just to detail back pressure a little bit more. So if you have, let's say, a producer and a consumer model. So you have a producer that's making events and a consumer that is consuming those events. Maybe they're communicating over a socket. So back pressure is needed when the consumer of a data stream cannot keep up with the producer. The producer is making too many events to be consumed. The consumer cannot consume them at the rate that the producer is making them. The consumer typically has a buffer to deal with these events being sent by the producer. What sorts of situations in an application are associated with back pressure, and what has to happen in the relationship between the producer and the consumer to deal with that situation?
Mm-hmm. So maybe first, when these situations actually happen.
Yeah.
And it's a very interesting shift in thinking so for example, we very often have customers or users on the mailing list that went from normal blocking applications. For example, they have some servlet in which they did everything blockingly, and now they want to scale out a bit more, so they come to Akka, and now everything is asynchronous because that's our default. And well, at the first moment there is asynchronous communication, we get into this situation that there is a producer and there is a consumer, even if you don't think about it explicitly this way, right? Because even if, in the case of actors, it's very explicit. There is a producer that is putting messages into a mailbox, and there is a consumer, which is the actor that is processing the messages in the mailbox. So there it's very explicit, which is also an upside of Akka because you can reason about it very easily. But even without Akka, just with threads, it's very much the same situation because, for example, if I'm scheduling asynchronous tasks on a thread pool, well, what happens if I'm crazily scheduling a lot of tasks on this thread pool and the thread pool can't keep up processing them? The same situation happens even if without thinking about messaging, just normal task submission. So the first moment you get into any kind of asynchronous programming, there should be some thought put into back pressure.
So in this situation where the consumer has this buffer that's filling up with events being sent by the producer, what typically happens when that buffer fills up with messages and the consumer can't take any more messages?
Yeah, so if we were to answer generically, then it depends. But let's start from the JVM answer. Well, you're basically out of memory and your system crashes because we have one shared heap for all the processes. That's, for example, if the producer and consumer are in the same JVM and we just talk about asynchronous messages between them. So then the entire app crashes. But the same situation could happen with a distributed application, that someone is sending messages or maybe consuming messages from a queue like Kafka, but consuming it and buffering it in memory, right? And then you try to process, but you can't really keep up. And then this process crashes, right? But eventually it ends up with processes crashing. What we have, for example, in Akka Streams is, so Akka Streams has built-in back pressure and it's enabled by default, which is a difference from RxJava. In RxJava, you have to think about back pressure and then, well, add it in a certain way. In Akka Streams, we thought that the moment you realize you need back pressure, it's kind of too late because things are crashing on production. So it shouldn't be an afterthought. So we just add it in there by default. And for example, whenever we have a buffer in Akka Streams, it has a specific behavior for the situation when it overflows. So for one thing, it shouldn't overflow because we have this backpressure mechanism, but you can put a explicit buffer there, and then you can say what it should do when it overflows. And the decisions are basically drop all the elements that you had in the buffer. So when you have a clean state, well, you missed some data, but at least you can survive now. Or maybe drop the oldest element that's still in the queue, or maybe drop the newest element. And turns out that this is actually sometimes even a business decision, what we want to drop from the buffer. So imagine you're subscribing to a stock ticker or something like that. And you have a buffer of stock value from the last, few minutes. And you keep getting new updates for the stock value of a certain stock. So if that buffer overflows, I simply can drop the oldest value of that stock because it's not really helping me right now. I need the newest value of that stock, right? So by making explicit decisions about that, we're able to model very interesting things that actually do loop a little bit back into the business decisions.
So I think we can get here into the discussion of reactive streams. What is a reactive stream?
Okay, so reactive streams, like I kept trying to get into the topic too early a bit. So it is a surprising answer to some people because it's a topic that's coming up online and there's presentations about them. And then sometimes people think, so I should be using reactive streams, which is both true and false at the same time. What I mean by that is, and when we started with the Reactive Streams initiative, we called it not API, but SPI. So we called it basically API for implementations thereof to communicate between each other. So, for example, RxJava would implement it internally, we would implement it internally, and this way we would be able to get an Rx stream and just directly connect it to an Akka stream, and the backpressure, which is defined in the Reactive Stream standard, would just work even though it's completely different implementations. So it was an explicit goal to be a interop protocol that's meant for libraries to implement, and then users would indirectly benefit from that. So what I mean by saying you should and shouldn't be using reactive streams at the same time is so let's say I'm at a company, I'm writing a project, I really shouldn't be implementing reactive streams directly because, well, it's a really, really low level concurrency protocol, I would even say, that's really hard to get right. So my part in that initiative was writing all the tests and TCK that would do all the crazy behaviors that we try to guard against. And really there's, well, maybe not hundreds, but at least 100 of crazy edge cases you need to watch out for when implementing reactive streams. So you don't want to implement reactive streams as a user of stuff because you want to get stuff done, and then you would spend months implementing reactive streams. Instead, what you want to do is know, okay, this library, it implements reactive streams, so I have these and these guarantees, the guarantees being the interop guarantee with other libraries, and the backpressure guarantee, which we can talk about in a bit in detail if you want to. But basically, it's guarantees that we will not overflow downstreams. So you knowing that a library implements reactive streams, that's all you need to know. I get these guarantees, I use that library, I'm good. But one shouldn't really be thinking about reactive streams as a library for user consumption.
Okay, so if I am writing an application where I need this interoperability, how does that impact what I'm doing? Is that like I can have one aspect of my program written in Java and the other aspect in JavaScript, and the reactive streams are the mechanism by which information is being communicated between Java and JavaScript?
Not quite. So reactive streams, actually, we have a reactive streams GitHub organization under which there is the reactive streams JVM, And this is what currently people refer to as reactive streams. So it's a set of Java interfaces, and people have ported it to, for example, Scala.js. So yes, it runs in JavaScript, but there is no bridge between, for example, the browser land into the JVM server side. However, this is something that we started a new endeavor on. So together with Ben Christensen of RX fame, who has been participating with us in Reactive Streams, the next step we want to take this thing is basically what you kind of briefly mentioned here, is taking this interrupt communication over the wire. Because currently it's strictly a asynchronous boundary protocol, so between threads. But we want to take the same semantics and take them onto the wire. That project is called the Reactive Socket, and it's mostly being driven by Ben Christensen, who is at Facebook right now. So that's the second step. But how does this interrupt story actually impact you if you have, daily job and you want to get stuff done? I think it's something that people don't notice, but maybe will notice soon enough. So for example, imagine you have a database driver, and the database guys figured, so maybe we should really provide an asynchronous driver because it would make sense. And what they would then provide is, well, as this database vendor, I don't want to lock people into a specific streaming framework. I want them, so the users of my database, to be able to consume my database in a streaming fashion with whatever library they like. So this driver would expose reactive streams. And then as a user of it, you would say, well, I'm using Akka streams and it just works. Or I'm using something else and it just works. Or again, if someone provided a nice streaming XML parsing library that's really streaming in asynchronous, or the same thing for JSON, they would expose the reactive streams interfaces, and then you're not locked into whatever library that author liked. You can consume it with whatever you like. So it really is the inverse of vendor lock-in. We really want to be the streaming kind of concept, a thing that everybody participates, and once someone has implemented a useful library, the entire ecosystem benefits.
So it's more like interoperability here means whether you are in JavaScript or the JVM, you have a similar experience when you are programming streaming applications. Is that accurate?
It's not quite about the different languages still. So we're still in the same JVM. So let's use the Java case. So let's say there's a reactive Mongo driver, right? And Mongo suddenly has a streaming interface, and they provided a reactive streams iterator, basically. So you can get a stream of documents from that Mongo file. And so reactive streams don't provide any kind of API that is actually nice to use. So it doesn't provide map, it doesn't provide filter, it doesn't provide any of the nice operators. It's just the minimal APIs that would allow you to make this back pressure work across libraries. So you need to use something to consume that stream, because you won't be, doing the low level thing all the time. You want to do a map and a filter on these streams. So you basically just take an Akka streams, connect it to this database thing, and it just works, and you get all these operators from the Akka streams library.
Okay, all right. So we're talking here explicitly about Akka reactive streams. I guess what I was confused about is I was thinking that reactive streams was something that you implemented it in Akka, and it's also offered in RxJS, and that's actually relevant here. But you're talking purely about the Akka ecosystem.
No. So Reactive Streams is a zero dependencies for interfaces library. And that has zero to do with, well, yes, we did mostly drive the initiative, but the RX guys and the Reactor guys and a bunch of other projects participated in that. And basically everyone agreed what we need as this minimal API that we can communicate between RxJava and Akka Streams and Redpack and RxNetty and all these different libraries. And they internally communicate over this library. So instead of everybody having a vendor lock-in, so if you use Rx, but someone in Akka ecosystem made a nice library, you can't use it because, yeah, it's different streams. You don't care which streams someone implemented the library with because, hey, it's a Reactive Streams compatible thing. I can just use it.
Okay. Well, let's talk a little bit more about the way that backpressure is handled in Reactive Streams. So there is a dynamic push-pull style of backpressure. Can you define what pull-based backpressure and push-based backpressure is and what the dynamic push-pull style for Reactive Streams is?
Yeah, so the dynamic push-pull style, maybe let's first talk about pull and why it's not enough. So in a pull-based backpressure mechanism, it's very simple to implement. It's super simple to implement. So the downstream, each time I processed a message, and I know, okay, since I processed a message, I'm able to consume another message. So I pull from the upstream, hey, now you can send me a message. The problem with that is a lot of overhead, right? Because for each message, you need to pull the next one and pull the next one. So this is why pull, it would solve the overflow problem because it is always safe because I as the downstream decide when I am ready to consume a next element. So we have solved the backpressure problem, but it's a lot of overhead. The purely push-based protocols are basically that the upstream decides, okay, I have data, I will push the data downstream. And I, as the downstream subscriber, may or may not have space in my buffer, and then I need to do something with the buffer that is overflowing, right? So the strategies I talked about with dropping the buffer, dropping the oldest element, etc., that's a flavor of basically accepting the push, and then I deal with it somehow. So what we do in the reactive or dynamic push-pull mechanism is it's like a pull-based protocol, but instead of pulling every message, we basically give a permit to the upstream that, let's say my buffer space was 10 elements. In general, I can have 10 elements in my buffer, and currently I have 4 elements in my buffer. So I can tell to my upstream, hey, I'm ready to consume at most 6 elements. And this is done via a asynchronous message. And so I send this, I demand 6 elements. The upstream then knows it can send at most 6 elements because we have ready buffer space for it. So it starts sending those elements asynchronously. So let's say it has sent 3 already. They're flying into the buffer, they're in the buffer, but in the meantime, I, as the downstream, have processed the other 4 messages that I had previously in my buffer. And then I decide, well, I previously signaled that I'm ready to consume 6 elements. I currently processed all of the 4 elements that I had in my buffer. So I didn't tell the upstream about these 4 spaces in the buffer that are currently free. They are available for buffering. So right now I can send to the upstream asynchronously again that, hey, now I demand 4 elements. So in the upstream, it can basically sum up the total number of permits, so the total number of elements it is allowed to send downstream. And if, for example, if it's spinning in a loop, it can keep spinning in this loop and producing the elements as fast as it can to push them downstream. And it will never overflow the buffer because it will always stop whenever it has reached the maximum number of elements it was allowed to send. So the key feature is that all of the communication, so the sending of a demand and sending of elements, is all asynchronous. So in the happy case, we never have to stop. But it's also safe because the upstream can never send more than it was allowed to.
Got it. What do I need to know about the lower level network protocols like TCP or UDP or HTTP or WebSockets in order to understand reactive streams more thoroughly?
So that's a good question. And it's also one of the confusion points about reactive streams. So it's a great question to ask here. So TCP, for example, TCP has back pressure built in. It has flow control. It has the so-called TCP congestion window. So it basically says which bytes it has received. So the sending side of TCP doesn't have to resend those, right? So if we stop advertising to the sending side of TCP that we have received these messages, or you can send this and this much data to me, then the upstream is basically being back pressured over TCP, right? So TCP always had that feature. However, in recent years we have been building in all kinds of web servers was we have this back pressure on the wire, so between the client and the server, but we didn't propagate it all the way through into the application. So for example, imagine this case that I'm Twitter and I'm streaming tweets to a mobile phone, right? And this mobile phone suddenly goes into a tunnel. So it stops receiving the tweets. However, the server keeps generating the tweets, right? It keeps crunching them, generating the live data for us, but it really doesn't have to. It doesn't even have to parse or prepare the tweets because the downstream, so the mobile client, is in a tunnel and won't be receiving the tweets anyway. So what reactive streams allow us to do is to take these TCP mechanisms and take them and expose them all the way up to the application so the TCP streaming server can realize, oh, the client is in a tunnel, so I won't be even generating the tweets for him because he won't be receiving them anyway. And when the client comes back, the TCP back pressure again picks up and starts consuming the tweets. Then the server is being woken up and starts generating tweets again. And this is pretty much transparent just by the fact of using any Reactive Streams compliant library. You don't even have to think about it.
Mm-hmm. Okay, I want to begin to zoom out and as we draw to a close in this conversation, what should people be taking away from this discussion? Is there something about the way that we write our applications that is changing that makes reactive programming more appealing as a paradigm for writing our applications?
Yeah, definitely. I think the biggest takeaway right now is that we have I would even say striving a nice ecosystem because we have these standards and everybody is cooperating with each other. So it's not like in previous endeavors where some library would do a thing and they would wall everyone off and you can't use this thing if you're not part of that ecosystem. Now we're in this wonderful point in time where all of the ecosystems start to converge because this idea of streaming data is so ubiquitous that basically everybody wanted to participate, and instead of fighting each other, all the libraries kind of joined efforts. And I think that's a really good time to, pick up on it because, that's a huge ecosystem and it's still growing.
So one aspect of one thing I read about is that there's this growing movement called No ETL that is trying to move us more towards stream processing and less batch processing. And there's some association here between reactive streams. How do reactive streams fit into this paradigm shift?
So again, like we talked in the beginning, that reactive is a very overloaded term. Sadly, streams is a overloaded term as well. So, for example, people would say, well, for one thing, there's the Java streams, which aren't streams at all. They're just parallel collections. So that's one offender. Then we have Spark streaming, which almost is proper streaming, but it actually is just very small batches. And then we have new libraries like Flink that are actually really streaming data processing and streaming data analytics. And then we have Reactive Streams, which are, like I said, a purely local abstraction. You can think of them like a overpowered iterator, really, an asynchronous, back-pressured, safe iterator. So in a way, it is very hard to compare when someone asks, could you compare Reactive Streams with Spark streaming? Because yes, the word is the same, but the goals are completely different. So this is something that we have a new challenge in defining terminology right now, I think.
So how are the ideas around Reactive Streams changing the JVM ecosystem?
Yeah, that's a great thing. So, like I said, it is a standard that multiple organizations participated in, including us and the Pivotal guys and the Red Hat guys, etc., etc. So, and it wasn't really done through the usual JCP process that would have taken, committees voting on APIs and ballots and stuff like that. But it was really a need of the entire Java community to come up with this common API that all of us felt we needed. And then it turned out that it's so useful that it's worth to include in the JDK. So now it's not only a random library that everybody is implementing the APIs, but it actually will be included in JDK 9. It will be the Java util concurrency flow, and that's basically a copy-paste of the Reactive Streams interfaces. So it also shows that with enough cooperation and need to do something important, we're able to move the Java ecosystem forward in ways that we previously thought is impossible.
So there are all these companies that are using Reactive Streams and contributing to the projects: Netflix, TypeSafe, Red Hat, Pivotal. Could you just close off by maybe talking about why Reactive Streams are relevant to these different companies, how they are using streams in production?
Mm-hmm. Yeah, so I'll start with 2 sentences about us and then the other guys, because I have most context about us. So the reason we came up with why we need this was basically, so TypeSafe is also the company behind, currently Lightbend is the company behind the Play framework. And in Play, there was a way to do streaming APIs, and that was very Haskell inspired. So then it wasn't a very good fit. Then in Akka, we also had some back pressure protocols, but they were a bit hard for users. And then we talked with Ben Christensen, and we kind of converged that, hey, it seems that we all need the same thing, which is slowing down the rate of producing if the downstreams can't keep up. So, for example, in the case of Akka, it would be that, it's great that Akka is so fast and we do so many millions of messages per second, but by the end of the day, we are hitting this legacy system over there with a few million messages per second, and we basically keep killing our own systems in some company. So we really needed a way to do as fast as we can, but not faster. And then it turned out that many other companies, and like I said, the RX guys, the Netflix case was exactly that. They were having trouble with, let's not kill our own servers, right? And turns out everybody was tackling the same problem, which is why the movement came to be and everybody participated.
All right, Konrad. Well, thanks for coming on the show. This has been an illuminating conversation about Reactive Streams and Akka, and I'm really glad to have had you on.
Yeah, thanks for having me.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow!